Hello, this is Dr. John Galaska, hoping to bring you a little bit of relief about Chapter 15, Statistical Evaluation of Data, in our textbook for PSC 5301. There are some learning objectives listed on page 441, and I just wanted to go through those very briefly. I won't be able to go through everything in the chapter, but perhaps I can ease your mind about some of this material that you may not be familiar with. If you're looking at it for the first time, some of it might seem a little bit overwhelming. Define the two general categories of statistics, descriptive and influential. Explain the purpose of each. Descriptive statistics simply does describe. It works with knowns about a sample. Okay? Descriptives works with knowns, and they describe usually a sample. Measures of central tendency, an attempt to describe a distribution with one data point or one figure, and measures of dispersion such as the standard deviation, the range. Those are descriptive statistics. Inferential statistics have to do with guesses. They usually refer to a population. So you could say, and the numbers that are generated when you're working with a sample are known as statistics. The numbers that are generated when you're working with a population, the guesses, are known as parameters. Okay, so you could say that a statistic is to a sample as a parameter is to a population. A statistic is to a sample as a parameter is to a population. If you want to make it a little more complex, you could say a statistic is to a sample is to descriptives as parameter is to a population is to inferential. Okay? Descriptive statistics, that genre has to do with knowns. The numbers are called statistics. Inferential, the numbers dealing there, the numbers that are generated there are known as parameters. They are guesses about a population. Okay, I've just defined a statistic and a parameter. And now we go down to number 3. Frequency distribution is simply a table wherein you put a list of the occurring data points, and to the right of the occurring data points, you put the number of times it occurs. For instance, if the score 75 occurs 5 times, you would have your list of scores on one side, and then next to the 75, you would have the number 5. That simply shows the frequency of the occurrence of that number. That's pretty straightforward stuff, frequency distribution. Define and compute 3 measures of central tendency, mean, median, and mode. Okay? An attempt to represent a data set with one number. Use the mean when the data is evenly distributed. Use the median when it is skewed. And the mode is simply the data point that occurs most frequently. You can have a multi-modal distribution. Okay. Explain how the mean and the standard deviation describe a distribution of scores. Well, the mean is a measure of central tendency. You can have 2 evenly distributed distributions, one that ranges, say, from 5 to 100. There you have a range of 95, and the mean could be 50. Okay. Now, you could also have another data set that goes from 40 to 60, and the mean is also 50. So here we have 2 very different distributions, one with a range of 95, one with a range of simply 20, from 40 to 60. And they both have exactly the same mean. So we can add the standard deviation to this mix to get a better understanding of what that distribution looks like. We could add the range as well, but if we add the standard deviation, that's going to tell us how spread out the data is. Which one of those distributions would be tall and skinny? Would be the one with a range of only 20, from 40 to 60 with a mean of 50. Which one would be low and flat compared to the other one? Well, this one has a mean of 50, but it has a range from 5 to 100 of 95. Which one has a larger standard deviation? Well, the one where the data is more spread out, the one that goes from 5 to 100. Here's something that you should memorize that's not in the book. The standard deviation is the average distance of every data point from the mean. The standard deviation is the average distance of every data point from the mean. You should memorize that. I will do a video on calculating the standard deviation. There are plenty of calculators online where you simply can plug the numbers in and hit calculate. It gives you all the descriptive statistics as well as the standard deviation and the variance. And all you have to do is input your data. One of them is called Calculator Soup, if you want to look that one up. I will try to make sure that I have that in the website for you. Marvelous thing, calculators and computers, love them to pieces. But I will show you how to do the standard deviation manually, once at least by video. But that's a good thing to know how to do. Now, what is the standard deviation? It is the average distance of every data point from the mean. Standard deviation is the average distance of every data point from the mean. Please memorize that. You may win a trivia sometime. Bang! Standard deviation is the average distance of every data point from the mean, and it's a measure of dispersion. Okay, so good luck with that. Now let's go here to explain how the Pearson correlation describes the relationship between two variables and predicts the general appearance of the scatter plot. Okay, correlation coefficient is simply the relationship between two variables. Vertical axis, horizontal axis. One variable on one variable on the other. Now, supposing on the left you have a number of ice cream sales going from 0 up to 150. On the right hand, on the bottom one, going from the vertices, that's where the axes meet over here, out to the side, you have number of drownings going from 0 up to 25. Now, consider this. When ice cream sales are very high, up here, right over there, the screen's weird, right over there, ice cream sales are high, guess what's going to happen to drowning deaths? They're going to be high too. Okay, so you're going to have a dot up in the upper right-hand quadrant. When ice cream sales are very low, you're not going to have very many drownings. What's going on here? It appears that there is a correlation between ice cream sales and death by drowning. You may have guessed it. When it's very hot, people buy more ice cream. When it's very hot, people tend to get in the water. When people get in the water, some of them do drown. So we have something that varies together, ice cream sales and accidental deaths by drowning. Of course, there is no causation here. No causation. To establish causation, you need to have a true experiment. We have correlation here, and this is what's known as a spurious correlation, because there is absolutely no relationship in reality between number of ice cream sales and number of deaths by drowning. They both vary according to the temperature. And there is a very real relationship between temperature and ice cream sales, and temperature and deaths by drowning. Okay, that is called a third variable problem of correlation. Now, in many correlations, you do not have a temporal relationship. They can both occur at the same time. One can occur before the other or after the other, whatever. If you do have temporal correlation, you can perhaps show some causality. It's a bit limited. But if you have a temporal relationship, for instance, if you give someone a study guide and then they take an exam, and the more they use the study guide, hours of studied, the higher their score on the exam. So these things vary in a causal way. One occurs before the other. That is an attempt to show causation with correlation. In this case, you have what are called predictor and criterion values. The predictor variable in this case, or value, is the length of time used in studying, and the criterion variable is the score on the test. So with correlation, if you have a temporal relationship, the one that comes first is called the predictor variable. The one that you're measuring that changes because of that is called the criterion value. Kind of like independent variable and dependent variable, and not really the same. It's not an experiment. You cannot, it's very difficult to prove causation with it, but you can attempt to hint at it. Okay, if the scatter plot, which means you put in all the dots from all the ice cream sales and all the dots from all the deaths by drowning on the plot, if you get an ascending bar from left to right, an ascending line at about a 45-degree angle, the closer that cluster of dots is to a straight line, the closer the correlation is to 1-to-1. If it is a 1-to-1 correlation, you will have a straight line. And that line has a special name, regression line. Regression line. If it goes from left to right, rising, it's called a positive correlation. Now, things are not always related that way. Sometimes, in a positive, they both go up together. In a negative correlation, one rises as the other falls. Let's just say time spent watching video games and scores on homework. The higher you spend, the more time you spend watching video games, often the lower your homework results will be. So in this case, you would end up with a scatter plot that starts high on the left and descends to the right. So if it is descending from left to right, it is a negative correlation. One goes up while the other goes down. Correlations are always expressed as a number between -1 and +1. You can have a 95%, a negative 95% correlation and a positive 95% or 0.95 correlation. Which of these is greater? Neither. They're exactly the same. 0.95 is correlation. It's just that they are in a different direction. One is negative correlation, one is positive correlation. If there is no correlation when you do a scatter plot with your two variables, you're going to end up with just data all over the place, something like a circle. Okay, so you should be able to look at a scatter plot, and I think there's a couple of them in the textbook you can look at. If the dots on the scatter plot are rising from left to right, the closer they rise in approximation of a straight line, the closer your positive correlation. If it is descending from left to right, the closer it is to a straight line, the higher your negative correlation. Zero correlation would mean just a bunch of dots all over the place, maybe in a circular pattern. That's a scatter plot. You might be able to find a YouTube video about that. That could be helpful, maybe fill in some of the gaps of what I haven't told you. Identify the general purpose of hypothesis test and how the test accomplishes the researcher's goal. I'm going to make another video or post a video about hypothesis testing, the steps that are involved, and I'm going to let that video explain this process to you. Identify the characteristics that differentiate different sets of data. Noir. Noir. French word for black or gray. In France, there's a writing school called Cadre Noir, Gray Guard. It's in Saint-Maur, France. Second oldest writing school in the world. The oldest one is the Spanish writing school of Vienna. Cadre Noir, gray or black. Hey, we're getting into the black area of statistics. Oh my gosh, fear and trepidation. Just a second, I'll be right back. Got to get some. I have a prop for this. Now, getting into the dark area of statistics. Dr. Galaska here. Noir, N-O-I-R. Put 4 capital letters on your paper somewhere. Draw a line between the O and the I. The N stands for nominal. That's categorical data. The O stands for ordinal. That is also categorical data. The two of these are discrete. You can't fit anywhere in between. If you were to make a set of eye color in our class, you'd have so many blues, so many greens, so many browns, and perhaps just another color. Sometimes people have an eye of one color and the other eye is a different color. Haven't met anybody like that, but I did see someone with purple eyes. Unfortunately, they did have a disease, so it wasn't such a good situation. There isn't any space between brown and green on a continuum, nor is there any suggestion that brown should come before green or blue. They can go in any order you want. If you were to graph the distribution of these brown, green, and blue eyes, you would make a bar representing the number of brown eyes. It would go up, say there were 10 in our class, and blue eyes, separate from this other bar, important, separation is important, would go up to however many blue-eyed people you had. Maybe we've got 5. And then green-eyed people, maybe we've got 3. I don't know. Okay? Bar graph is used to represent nominal data. The bars do not touch each other, and it's called the bar graph. And this data is called discrete because it has to go in discrete categories. Okay, it is not numerical data. Now, on the other side of the line, you have interval and ratio. This data is continuous. You can slice it and dice it. You can operate with it mathematically. You can do mathematical procedures with it. I stands for interval. It goes infinitely in the positive direction and infinitely in the negative direction. Ratio data can be treated numerically as well. You can do mathematical operations with it. But ratio data has something that interval data does not. Ratio data has a true zero. Height, ratio data, there can be no height. Weight, true zero, there can be no weight. Therefore, height and weight are ratio data. Both interval and ratio data are considered continuous. And the reason for being aware of the types of variables that you have is the kind of statistical analysis that you would do with these is different. I'm going to give you a decision tree that has decisions about how many groups you have, whether it's within subjects or between subjects, and the type of data that you have, nominal, ordinal, interval, or ratio. And if you answer these questions, you will come to the right-hand side where it will give you the kind of statistical procedure that you should use for the data at hand. I will post this decision tree in our resource section. Okay, so we are into the noir area of statistics, the black area of statistics. Sure, am I having fun or what? Okay. I hope that helps a little bit. Now, let me get to these others here. 2 basic concerns with the calculation of split half reliability. You're going to have to look for those 2 concerns in the book. But I can tell you about split half reliability. Split half reliability has to do with an assessment instrument. Supposing you have 100 questions in that instrument, split half reliability refers to taking every possible combination of half, jumbling it up, half over here, half over there, scoring each of those halves, and seeing the relationship correlation coefficient, which is called Cronbach's alpha. An alpha of 0.7 is considered adequate. Split half reliability, sometimes called internal consistency. If your numbers are lower, if your correlation coefficient between one half and the other is less than 0.7, you have inconsistencies. You have some items in that test that do not contribute to the effectiveness of the test. So split half reliability has to do with how one half agrees with the other. Inter-rater reliability and Cohen's kappa, you're going to have to look Cohen's kappa up, but inter-rater reliability simply refers to the fact that if I give a test to the class, we get a certain result. If I'm out one day and I have a substitute, someone else comes in and gives the exact same test, there should be a very close relationship between one and the other. That's from rater to rater. Now, the interesting thing, inter-rater reliability is not always a given. For example, if the person who is administering an achievement test is white, middle class type, whatever, person, black children tend to score lower. If the administrator of that same test is black, black children tend to score higher. So inter-rater reliability is not always a given. Sometimes you have cultural play in there that will affect the results. Okay, I hope I've given you a little bit of stuff to ease your mind about this awesome chapter 15 in the book. Remember, I am down in room 119, 118 down there. Kind of swapped rooms there because one of those classes is pretty big. Look for me down there around 5 o'clock on Tuesday evening and Wednesday evening. Stop in and say hello if you'd like. If you have any questions, you can come in and bring them to me. You can also email me as well. I hope the questions and the quizzes that you're doing are helpful in getting you to become familiar with the concepts that are in the textbook. And I know that some of the stuff is very dry and tedious, so my feelings go out to you. It will be of utility to you when you get into the field. And some of you will go on for doctoral study, and you're going to need to know this good stuff about research methods and a bit about statistics in order to do well. Okay, Godspeed. Take care. Dr. Galaska back with an old friend of mine. It's the meditation frog. This frog actually sings Om. Isn't he a nice looking frog? I forgot something, and I need to tell you about two things that I scrolled over that are learning objectives in this test. The first one has to do with the relationship between the number of items and the number of data points you have in a set when you are doing a statistical analysis. There is a thing called the law of large numbers, which you probably read about. Generally speaking, the more data points you have in your set, the more data you have, the easier it is going to be to find statistical significance. However, that is not always a good thing. Sometimes, if you have, let's just say you've got a study guide. I keep bringing that study guide up. I'm going to have to write one of these days. A study guide, and we give it to 10,000 subjects. And we find that their average grades, people who had the study guide versus the people who did not have the study guide, was 1/4 of a point higher. And because we had so many subjects, 10,000, it turns out to be statistically significant. So you can prove something to be statistically significant that has absolutely no clinical utility at all. What difference does it make if somebody scores 0.25 higher because they had a study guide? Might as well just leave it out. You're only going to score, on average, 0.25 points less. That's a problem with big numbers. Okay, so what happens if you have 2, 3, 7, 12 subjects in a treatment and you're trying to prove that your hypothesis, that your treatment works? Well, if you add 1 or 2 data points that don't really fit well into this set, you're going to change your results dramatically because the set is so small. So what's a good number? A good number is 16. Okay? A good number to have in your research study is 16 or higher, anywhere up to about 100. Now, the reason for this is explained on page, I think it's 136 in your textbook. It's a good explanation in there. Between 16 and 100, you have a good basis for assuming normality of the distribution. As you get higher than 16 and approach 100, the ability to predict statistical significance does not increase dramatically. It diminishes with the more subjects you get. This is a characteristic of the nature of hypothesis testing. So you might think 10,000 subjects, whoa, great study. Statistically significant results were found that proved that, that my study guide will get you 0.25 points higher on the final exam. Large numbers, statistically significant mathematically, of no use clinically. Okay, that can happen. Generally speaking, if you have the consequences of making an error make a big difference. If you are working with pharmaceuticals and one of the side effects is death, you might want to have a lot of subjects. Be very, very careful about what you're doing. You would probably want to increase your level of significance. You'd probably want to lower it to 0.001. We'll talk more about that another time. That means that 99.9 times you would be correct in your prediction if it was proved statistically significant at that level. If you have a 0.05 level, you would be 95 times out of 100. Simply by chance, you would be correct in making your conclusion. It's called your confidence interval. You subtract the p-value, or the level of significance, from 100, and that will give you your level of confidence. So p-value of 0.01, 99%. P-value of 0.001, 99.9% confidence. P-value of 0.1, 90% confidence level. Okay, now the more variation you have in your data, the more difficult it's going to be to prove statistical significance. If your data is clustered closely around the mean, it's going to be easier. Type 1 and Type 2 error. I always make myself a diagram for this, and I hope that you'll be able to see this. Let's see what I can do here. On my handy-dandy whiteboard, we don't want to get too much of a reflection on there. I always make a square. It's just easier for me to do it this way. Yeah, let's see which one is it better. Okay, up at the top, you're going to put true and false. And this refers to the null hypothesis. Talk to you about that in a second. This refers to the two possibilities you have with the null hypothesis. You accept or you reject. Now, the null hypothesis simply says that whatever your treatment hypothesis is, it doesn't work. And I can see that I'm looking at this thing backwards. I hope that you're not looking at backwards too. Maybe you want to watch this video in a mirror, or hold the mirror in front of you and watch the video. I don't know. Well, maybe I can reverse this thing somehow. At any rate, the null hypothesis simply says that whatever procedure you're using does not work. This is a statistical gimmick that has to do with the ability to prove something wrong. If I say that my study guide works 100% of the time, and I find one case where it doesn't, I've just proved that that study guide does not work all the time. It's easy to prove something wrong. It is difficult to get every possible situation and test it and show that it conforms every single time. So the null hypothesis is a ploy that is used in statistics, and the null hypothesis is what we deal with in statistics. We accept or reject the null. In your journal article critique, you're going to be required to identify the null hypothesis. Now, the null hypothesis is not going to be found in the article. You have to construct it. The reason I'm having you do this is because statistical analysis and hypothesis testing works with the null hypothesis. If your hypothesis is that my hypnosis treatment mediates depression, I could concretize that and say my guided mindful meditation style hypnosis with heart rate variability, resonant breathing involved lower scores on the Beck Depression Inventory. That is my alternative or my research hypothesis. If you were to diagram it, you would call it H1, with a little H with a little subscript next to it. The null hypothesis would be that my guided mindful meditation hypnosis doesn't make any difference. Okay, that's the null hypothesis. Whatever your hypothesis is, saying it doesn't work is the null hypothesis. So here's a couple of possibilities. Either your null hypothesis is true, my hypnosis does not work, or it is false, and my hypothesis does work. There's only two possibilities in statistical analysis for what happens with a null hypothesis. You either accept it or reject it. Now, if you accept a true null, you are correct. If you accept the null, that means your treatment doesn't work. What do you think the researcher wants? He wants his treatment to work. He wants to reject the null hypothesis. Now, if you have a true null and you reject it, you've made a type 1 error. If your null hypothesis is false and you accept it, you have made a type 2 error. If you reject a false null, then you are correct. So construct a little quadrant like this, put true and false on the top, accept and reject on the bottom, and remember that this true and false refers to the quality of the null hypothesis, whether it is in fact true or false. And the only two possibilities that you have are to accept or reject it. Roses are red, violets are blue. If you were a null hypothesis, I would not reject you. Okay, I hope this helps a little bit. You could probably find a good little YouTube video if you Google YouTube tutorial on type 1 and type 2 errors. Remember that what a researcher wants to do is to reject the null hypothesis. If you reject the null hypothesis, you accept your alternative hypothesis, which is your research hypothesis. And in the example I gave, it is hypnosis. Okay, I had to add a little addendum to our video here. Godspeed, take care.